Hey y'all, this is Jesse with Green Take. This video is a quick overview of zeroing a pistol-mounted optic, understanding manual offsets, and calculating manual offsets at different distances. If you'd like, you can skip forward in the video using the timestamps in the description below.
I tried to find a good definition for manual offset, but I didn't really find much, so I came up with my own. If you can think of a better way to word it, please let me know in the comment section below. The best I could come up with is, a manual offset is the amount that you'll need to change your point of aim to achieve a desired point of impact at a particular distance from the target. And I realize that may sound a little bit convoluted, but it should make sense here in a few minutes. Before I get into manual offsets, it is important to understand what zeroing is and what it isn't. A common misconception is that zeroing a firearm will result in a point of aim which is the same as a point of impact at all distances. The truth is, zeroing only gives you a point of aim which is the same as your point of impact at one distance, the distance you zeroed from. Any shot taken inside or beyond that zeroed range will impact slightly higher or lower than your point of aim. A manual offset is a way to anticipate that deviation and account for it as you take aim at your target. In a perfect world, we would be able to look down the back of our firearm, through the barrel, and onto the target. However, that is completely impractical. Instead, we look over the top of our firearm. This gives us two separate planes when you shoot, the optical plane and the plane that the round is traveling on. It is important to note that this presentation does not take gravity into account. While gravity does play a major factor, that gets into more complex ballistics and is too broad for this presentation. When we add an optic to our pistol, the distance between those two planes is even more extreme, as the optic sits higher on the pistol than the iron sights. To account for the distance between the two planes, we zero our firearms so that the two planes will intersect at a predetermined distance. But, as I mentioned earlier, that intersection only occurs at the distance from which the firearm was zeroed. As you can see, using the same 25-meter zero, if we were to move the target in to 12 meters, the round will impact slightly lower. And, inside of 7 meters, where statistically speaking most incidents occur, the round will impact quite a bit lower than the point of aim. The good news is, using some basic math, we can calculate exactly how low or how high the round will impact at a given distance and aim accordingly. This slight modification of our point of aim, in order to achieve a desired point of impact, is what's known as a manual offset. To calculate how much of a deviation we should anticipate at a given distance, we first need to know the exact distance between the optical center of the optic and the center of the muzzle of the firearm. To get this measurement, you'll need a few bits of information. The first bit of information that you'll need is the distance between the bottom of the optic and the optical center. Many manufacturers will give you this information, but if you need help finding it, feel free to reach out to us and we can help you out. For this example, we'll be using a Trijicon RMRcc. Trijicon lists that measurement at 0.528 inches. The next bit of information you'll need is the distance between the top of the slide and the center of the bore. Be sure the firearm is unloaded and preferably disassembled before you get this measurement. For our example, we'll use a Glock 19, which has an approximate measurement of 0.39 inches. The last piece of information you'll need is the depth of cut for your optic. If we cut your slide for your optic, we'll gladly provide this information to you. If not, you can get that measurement by using a depth gauge to measure the base of the optic cut to the very top of the slide. When you add all three of these measurements together, you should come up with a total measurement of 0.728 inches. For this example, that will be the offset that we use. Now, let's say you didn't recess your optic and you decided to go with a dovetail mount instead. As you can see, there is an additional ½ inch of difference between the two planes. It might not seem like much up close, but inches add up to miles when you're shooting. If you are inclined to buy a dovetail mount, call us instead. We offer great prices, fast turnaround times, and if you use the promo code in the description below, we will give you 10% off your order. Now that shameless plug is complete, you can see that with a recessed optic and a 25-meter zero, you will only be about 0.146 inches low on a target which is 20 meters away. You'll be about 0.291 inches low if that target is 15 meters away. You'll be just over a ½ inch low if the target is 7 meters away, and at point blank range, you'll be just under 3/4 of an inch low. By this point in the video, you should have a basic understanding of what a manual offset is, how to reduce a manual offset, and what to expect when you're shooting. For the remainder of the video, I'll be going over the math involved in calculating an offset at different distances. If you would rather not watch this video because you're too eager to visit our website, I completely understand. Just do us a favor, like, comment, and/or subscribe to our channel. If you want to spend the next few minutes doing some basic trigonometry, stand by. For this example, we will use the same pistol and optic combo, but we will set our zero distance to 7 meters. As you can see, a 7 meter zero gets you up on target much faster, but it results in a more dramatic positive offset on targets past 7 meters. The first thing we need to know is the angle where the point of aim and point of impact intersect. We can determine this angle using the following formula. The unknown angle is equal to the inverse tangent of rise over run. Our rise is the calculated offset from earlier in the video, 0.728 inches. Our run is the distance at which we zeroed. The distance needs to be converted into inches. Our 7 meter zero works out to be 275.59 inches. Plugging those numbers in, the unknown angle is equal to the inverse tangent of 0.728 over 275.59. This gives us an angle of 0.1514 degrees. Using that angle, we can now calculate the offset for a target which is 50 meters away. To do so, we will use the following equation. Tangent to the angle is equal to offset over target distance minus zero distance in inches. From the previous step, we know that the angle is 0.1514 degrees. We don't know the offset, that's the variable that we are solving for. We know that the target distance is 50 meters away, minus the zero distance, which we calculated at 7 meters. The target distance minus the zero distance gives us 43 meters. 43 meters works out to be 1,692.91 inches. To get the unknown variable, the offset, by itself, we will multiply both sides by the denominator, 1,692.91. This gives us a final positive offset of 4.47 inches on a target which is 50 meters away. To show that the formula works for all distances, I'll go through two more quick examples. Using the same angle, we can now calculate the offset for a target at 7 meters. Of course, 7 meters was our zero, so the offset should work out to be 0 inches. To do so, we'll use the same equation. Tangent to the angle is equal to offset over target distance minus zero distance in inches. We know the angle is 0.1514 degrees. We will pretend we don't know the offset. We know that the target distance is 7 meters minus a zero distance of 7 meters. Target distance minus zero distance gives us 0 meters. Again, to isolate the unknown variable, the offset, we'll multiply both sides by 0. Any number times 0 works out to be 0. In this case, our offset is 0 inches. For our last example, we will use the same angle and a target distance of 0 meters. Because we are at 0 meters, our offset should be 0.728 inches. We will use the same equation. Tangent to the angle equals offset over target distance minus zero distance in inches. We know that the angle is 0.1514 degrees. We will pretend that we don't know the offset. We know that the target distance is 0 meters minus the zero distance of 7 meters. The target distance minus zero distance gives us negative 7 meters. Negative 7 meters works out to be negative 275.59 inches. When we multiply both sides by the denominator, negative 275.9, we get a final offset of 0.728 inches. And actually it works out to be 0.72822 something. But rounding off, we're exactly where we should be.
We appreciate you taking the time to watch this video. If you have any questions, please feel free to comment in the comment section below, or you can reach us on our website, www.greenticktactical.com.